Hello, my name is Anastasia Antropova, and I'm a chemistry major at Holyoke Community College. I am presenting my research project, Give It the Green Light, evaluating microwave synthesis of aspirin for environmental impact. The reaction that I studied was the synthesis of aspirin from salicylic acid and acetic anhydride using various catalysts and heating sources, primarily a microwave. So why use a microwave? Microwaves have gotten some hype for their use in green chemistry, especially due to their energy-saving potential. They open the door to unconventional reaction mechanisms due to unique conditions impacting temperature, dipole orientation, and activation energy. Since microwaves can raise temperature quickly, increase organization, and stabilize transition states, they can increase the rate of successful molecular collisions. This decreases reaction time and increases yield and purity. As a result, microwaves serve as a kind of mechanical catalyst, all on its own. Given the theoretical benefits of microwave synthesis, I decided to use a microwave to synthesize aspirin, including trials with no catalyst, phosphoric acid catalyst, calcium carbonate catalyst, and a sodium acetate catalyst. I also prepared aspirin using the traditional method, with a phosphoric acid catalyst and heating provided by a hot plate. This experiment was inspired by the paper A Greener Approach to Aspirin Synthesis Using Microwave Irradiation, which is included in my references. Here you can see an image of my collected crystal products for each trial. The goal of my project was to compare each of the trials based on their relative environmental impact. To do so, I created 4 primary criteria based on the American Chemical Society's 12 Principles of Green Chemistry. These criteria are waste reduction, safety, energy efficiency, and purity. Waste. Waste was measured using atom economy. This is a measure of the theoretical yield mass over the total mass of all reagents and auxiliaries used in a synthesis. A higher atom economy percentage indicates less waste, as more of the inputs were incorporated into the final outputs. Based on atom economy, the no catalyst trial produced the least waste. Safety. Using PubChem's records for each catalyst, safety concerns were noted, with the no catalyst trial being the safest, and the 2 trials using phosphoric acid having significant risk. Energy. Energy usage for the microwave and hot plate syntheses were calculated using equipment specifications and heating time data. The microwave trial only required 2 minutes of microwaving at 30% power, while the hot plate required 48 minutes total to come to temperature and to heat the reaction mixture. This made the microwave synthesis much more energy efficient. Purity. Purity was determined using 3 methods, the first being ferric chloride tests. Ferric chloride tests are initially yellow in color, then turn purple if exposed to phenol groups. The salicylic acid reagent will cause the test to turn purple, while the aspirin product will not, so the progression in color shown in the first 2 photos indicate a complete reaction. These tests were performed every 5 minutes after removing the reaction flasks from their respective heating method. The final photo shows ferric chloride tests performed on the crystal products for each trial. The phosphoric acid, sodium acetate, and traditional trials show some salicylic contamination based on the slight purple color. Purity was also determined using infrared spectral analysis. Scans of the crystal products show general agreement among all trials. When compared to a commercial Bayer aspirin tablet as a reference, they show that all trials produce aspirin that was relatively pure. A few odd peaks in the phosphoric acid and calcium carbonate catalyzed trials may indicate small amounts of byproducts or leftover catalyst. purity was also determined using melting point data, which confirms aspirin formation for all trials. Secondary evaluation criteria. I also compare the trials using some more conventional criteria, including percent yield, crystallization time, and relative cost by catalyst. For these metrics, the traditional method tended to perform slightly better, likely due to the extensive fine-tuning for that procedure. Conclusions. For conclusions, I found that the no catalyst trial was the most environmentally friendly synthesis method, mostly due to entirely eliminating a reagent. However, further improvements to the microwave procedure could increase yield, purity, and crystallization time, making this method on par with the traditional method. That being said, I hope that my project increases awareness about the sustainability of synthetic methods and that it emphasizes the importance of incorporating green chemistry into both education and industry. Here are my references. I would like to thank my mentors, Dr. Rubinski and Dr. Stengel at Holyoke Community College, for their extensive mentorship and support. Without them, this project would not exist. I'd also like to thank Mr. Derek Swist for his extensive assistance with materials and equipment. Finally, I'd also like to thank Professors Carpenter, Martinez, and Vasu for facilitating the STEM seminar program. And lastly, funding was provided by the National Science Foundation, or NSF, through the Holyoke Community College STEM seminar program. Thank you for listening.